This webinar,
especially for someone who's not super knowledgeable on temperature measurement. So let's get started. So temperature is one of the four most common measurements in a plant, along with pressure, flow, and level in a tank. It's often kind of looked at as the ugly duckling because it's not real exciting compared to other field instrument technology. You know, there's not a lot to it, but it's needed to monitor and control in every industry, and there's lots of applications because it's in so many industries, and usually they are relatively simple compared to other field instrument technologies. So our agenda today, we're going to go over the differences between the most common industrial temperature sensors, so RTDs and thermocouples. We're going to go over the advantages of using a temperature transmitter over direct wiring back to your PLC or control system. We're going to discuss how sensor matching can add accuracy to your temperature measurement. And then we're also going to discuss what needs to be considered when choosing a thermal well with your temperature sensor. All right, so we'll start with RTDs and thermocouples. So there are other types of industrial temperature sensors. So examples are infrared, liquid displacement thermometers, so mercury or alcohol-based, dial thermometers. But RTD and thermocouples are widely the most common industrial temperature sensors. So we're going to go over the differences and the advantages and disadvantages of both of them. So RTD stands for Resistance Temperature Detector. It operates on the principle that electrical resistance of certain metals change in a predictable way depending on the rise and fall in temperature. So its measurement, because it's a resistance measurement that's proportional to the temperature, it's measured in ohms usually. Sensors are typically made from platinum, nickel, or copper. Each metal varies in sensitivity, accuracy, and temperature. Platinum has the most stable resistance temperature relationship over the largest temperature range, so that is why it's typically used. So the most common RTD is a 100 ohm platinum, so notated as a PT100 typically. So PT100 has 100 ohms of a resistance at 0 degrees Celsius, so that's why it's called a PT100. Another example is PT1000, so it has 1,000 ohms of resistance at 0 degrees Celsius. RTDs come in 2, 3, and 4 wire configurations. So the additional wires limit errors from resistance imbalance of the lead wires. So lead wires are used to connect the sensor to a process control instrument and can cause measurement error. 2 has the most extreme error from this. 3 gets a little bit better, and 4 almost eliminates this error. 3 is typically what you find in industry and usually acceptable in terms of accuracy and everything. For industrial applications, you see 4 wires a lot in laboratories. So typically, most people have a 3-wire PT100 is probably the most typical RTD. So moving to thermocouples, how does that work? It's typically notated T/C, like you see in the title. So it's the way it works is it's 2 wires made of different metals, and then they form a junction at the tip. So 2 different metals form a junction at the tip. And that produces a voltage that is proportional to temperature. So that relates back to the thermoelectric effect. So it's measured in, whereas RTDs were measured in ohms because it was measuring a resistance, this is measuring a voltage, so it's measured in millivolts. So there's 4 base thermocouples, T, J, E, and K. Those are the most common. There's others as well, and they're usually notated by a letter. Type K is the most common, or each thermocouple is best suited for different applications, so they're usually selected on temperature range and sensitivity, so they all have advantages and disadvantages. Type K is by far the most common general purpose thermocouple, so that's one kind of like the PT100 for RTDs that you'll see in the field a lot. Usually the lead wires of thermocouples are color-coded, so you can determine the type of thermocouple by the wire colors. So it depends on national standards. As you can see from this graph, you know, every country is different, but it is kind of nice when you're out in the field, if you're trying to wire up a temperature transmitter, you could figure out what type of thermocouple you have just by looking at the lead wires. If you know this, you know, you can pull up this table on your phone maybe if you're out in the field with reception. So this slide goes over the temperature ranges for the thermocouples and RTDs that we talked about. So you can see in general, thermocouples have a a broader temperature range compared to RTDs. But, you know, RTDs, you can see, go from -325 to 1200. So for most applications, really an RTD should be suitable. It's only when you get to those extremes that you might have to go with a thermocouple. So the advantages of RTDs over thermocouples, generally they're higher accuracy. So that's kind of a big plus. You're always going to get a better reading from a RTD. They can provide a stable output from -325 to 1200 Fahrenheit, like we saw on that previous slide. They can be recalibrated for verifiable accuracy. So this is kind of two different ways. They can either be, you know, calibrated, just a verification to say, okay, you know, my RTD is within tolerance, but they also can be recalibrated, so provided a new characterization to establish a new resistance versus temperature curve fit. So this is, we'll discuss this in a later slide, that sensor matching that I mentioned in our intro. We'll discuss that a little bit more later on. They offer a long-term stability, so that's a lower life cycle cost, so you won't have to replace them as much compared to thermocouples. They follow a more linear curve than thermocouples, so that resistance versus temperature is very linear, and it has an accurate reading over narrow temperature spans. So when you really got to get, you know, if your measurement's really low in terms of like with a analog instrument, you're 4 to 20, the RTD is your best bet with that. So thermocouple advantages, so they operate at temperatures from -300 to 2300, so a little bit bigger range with thermocouples. They're good for rugged applications, so if there's significant shock or vibration, you know, you have a really, a line that vibrates a lot or just something happening where you can experience a lot of shock, it's good for a thermocouple. They have faster response times than RTD, so if you have a critical safety application, you might want to go with a thermocouple that has a fast response time. They have a small size, so the sheath can be at least less than 1/8 of an inch, so that kind of goes into that kind of affects the response time as well. And the initial cost may be less in some applications, so generally they're cheaper than RTDs. So the takeaway from all this is, you know, RTDs have a lot more advantages than thermocouples. Always start with an RTD if you're specifying a sensor. If process conditions don't allow you to go with an RTD, then go with a thermocouple. RTDs always are going to be a better bet. All right, moving on to our second topic. So we're going to go over why you should use a temperature transmitter over direct wiring the sensor back to a control system or a monitoring system. So traditionally, there's been two methods for getting temperature measurement readings back to a control or monitoring system. So the first one is direct wiring, so on the top of the slide. So you have a sensor in the process. Then you take sensor extension wires, provide a direct connection between your sensor, your RTD or thermocouple, back to your control or monitoring system. So they carry that low-level sensor signal, so the RTD or thermocouple signal that's in ohms or millivolts back to the control system. In the past, direct wiring was considered cheaper and easier, but we'll kind of go over why that might not be the case going forward. So the second traditional method is using a temperature transmitter. So it's usually installed at or near the measurement point. So this graphic here is sort of representative. So you got a sensor with a thermal well, and then the transmitter is directly mounted to the thermal well. That's pretty typical, or there might be a few feet of conduit isolating it from the process, but typically it's right at the measurement point. The transmitter amplifies and conditions the sensor signal, transmits it via a twisted pair cable. Transmitters previously were only used for critical applications because of their cost, but now temperature transmitters are comparable in price to direct wiring, especially when you have a long distance between your process and your control system. So we'll go over on the next slide what are the main reasons why you would want to go with a transmitter over direct wiring the sensor now that we understand the difference between the two. So the first reason why you should use a temperature transmitter over direct wiring, lower cost of wiring. So in the direct wiring scheme that we talked about, you need those sensor extension wires. The sensor extension wires are fragile, and they're much more expensive than typical 4 to 20 milliamp analog wiring. So the cost of the transmitter can be justified in wiring and conduit costs alone a lot of the times. Another way to think about it too is if you already have an existing direct wiring scheme, you can easily add a transmitter, a temperature transmitter, because there's no need to retrofit those sensor extension wires. The 4 to 20 milliamp analog signal could ride on those existing wires, and there'll be little installation time and cost because you can keep the wiring, keep the conduit. You just got to throw in a transmitter, and then you still get the high-level signal benefits of a transmitter. So benefit 2. Less signal interference. So most industrial environments have RFI, so radio frequency interference, and EMI, electromagnetic interference, that can affect process signals. So some sources of these interference are motors, high-speed switching elements, transformers, welders, radio and TV signals. There's many more as well. You know, a typical plant will have all those sources. So in a direct wiring scheme, those low-level signals from either an RTD or thermocouple, so those ohm or millivolt signals, are particularly susceptible to radio frequency interference and that electromagnetic interference. Also, the sensor extension wires can act as a kind of antenna to the radio frequency interference and the electromagnetic interference by drawing plant noise to the wires. So both of those things are, it's going to be really hard to have a long run between your sensor and your control system. So in the temperature transmitter scheme, it's going to convert that low-level sensor signal to a high-level analog signal, so this 4 to 20 milliamp signal, that's going to be resistance to that RFI and EMI. So it can do a long-distance transmission through a noisy plant without any problems. So the third benefit, decreased hardware and stocking costs. So in a direct wiring scheme, you're going to need specific DCS and PLC cards to match the sensor you're using. That's going to be expensive stocking those two. 4 to 20 milliamp analog input cards are usually a lot cheaper. So if you have a universal temperature transmitter, so that's one that will either accept an RTD or thermocouple, then all you need to stock is the 4 to 20 milliamp PLC and DCS cards, which is a lot simpler and a lot cheaper. So advantage 4, choose the best sensor for the application. So when you have the temperature transmitter scheme, if your application requires that you want to switch from an RTD or to a thermocouple or vice versa, all you have to do is just change out the sensor. The wiring and the input boards don't have to be changed. You just got to make sure you have a universal temperature transmitter that accepts both, and that's all you have to do. So there's a big advantage there. Number 5, increase accuracy and stability. So temperature transmitters usually have better accuracy. PLC and DCS systems usually use the entire temperature range. Transmitters can be scaled to a specific span, so you can span that analog signal to whatever the application is going to see. So you'll get better accuracy that way. And if you want even more accuracy, some smart temperature transmitters can precisely match the curve of a specific sensor. So even though sensors are designed to have a high degree of conformance to an established curve, like that resistance temperature curve that we talked about, each one will vary slightly from their stated specification. So the temperature transmitters can match that curve, and we'll talk about that in a little later. I know I've mentioned it a couple of times. We'll talk about that sensor matching in the next couple slides. So number 6, lower maintenance cost and time. Smart universal temperature transmitters have a lot of diagnostics to diagnose various failures like sensor failure and other process abnormalities. They're able to find whatever the problem is quicker. You'll move away from that fix it as it breaks mentality and do more preventative maintenance. So it's going to be more less downtime, less maintenance work, less cost. And also, smart temperature transmitters have a lot of other features like digital outputs, and then they can also output multiple variables. So if you have a dual input sensor, you can put that both into a transmitter and then output it. So the takeaway from this, as you can probably figure out, is whenever possible, use a temperature transmitter. There's a lot of benefits for it. Okay, so sensor matching. Temperature transmitters are kind of unique compared to other field instruments in that the sensing element, so the RTD or thermocouple, is separate from the transmitter. A lot of times the sensor and the transmitter are actually from different manufacturers, so you're integrating two different things. Other transmitters, like pressure transmitters and a lot of flow meters as well, you know, the sensor and the transmitter are all together. It's all made by one manufacturer and they're all integrated. This is a little, temperature transmitter is a little unique. Sensor matching, which is what we're going to talk about, allows you to achieve better accuracy between your sensor and transmitter, which will give you a better overall temperature measurement accuracy. So sensor matching is only available on RTDs. So I've mentioned it like when we talked about recalibration for RTDs. So smart temperature transmitters typically use some standards. So an example is IEC 751 to define the relationship between resistance and temperatures for RTDs. So we call this relationship the standard curve, which you see on the graph here. So sensor manufacturers manufacture their sensors to the same standard, but because of the construction process, each sensor has a unique temperature resistance relationship, and we're going to call this the real RTD curve. So the real RTD curve still falls within the tolerance band of whatever standard they're using, but it's just a little bit off of the standard curve. So in the 1920s, to give you a little history background on this, Hugh Longbourn Callender and M.S. Van Dusen developed a set of coefficients that would modify the standard curve to match the real RTD curve, thus removing the error generated by the difference between the two curves. So it's a form of curve fitting. The sensor manufacturer would provide the coefficients, and then you would put those coefficients into the transmitter, and the transmitter would do all the math to basically get this better accuracy. So these Callender Van Dusen's coefficients is one example. There's other methods as well. This isn't the only method for curve fitting for temperature. So many smart temperature transmitter vendors offer an option that can accept these coefficients to adjust the standard curve to match the real RTD curve of the sensor. Eliminating this error improves the accuracy of the transmitter sensor system. So if you have an application and you're looking for more accuracy, look at sensor matching with an RTD with your temperature transmitter. Okay, so thermal well considerations is our final topic today. We'll go into that. So first question, what is a thermal well? So a thermal well's main purpose is to isolate the sensor from the process. So, you know, typically a lot of times in plants and industry, the processes are dirty and dangerous, and you sometimes might need to protect your temperature sensor from experiencing that. So thermal wells provide various process connections. So you can see in the top picture, you can see all different types of process connections. There's flanged, sanitary connections for like the food and beverage industry, threaded, welded, so there's all different types of process connections that you can get. Thermal wells aid maintenance by allowing the sensor to be removed without having to drain the pipe or tank. Sensor changes can be done on the fly. So the thermal well is installed in the process. Usually the sensor is, you know, threaded into the inside of the thermal well, so you could take it out and replace it or do some work on it without having to, you know, open up your process. So it's a closed system. It'll increase the life of the sensor, and it'll save you money and maintenance time. So thermal well design considerations. So when determining thermal well designs, so when you're thinking about how far you want the thermal well to be immersed in the process, what type of connection to have, consider these modes of failures that the process can do to damage your thermal well or fail your thermal well. So pressure, static pressure on a line or in the process, make sure like if you have a flange connection, make sure that flange rating can withstand that pressure, or a threaded connection, same thing. Temperature, a similar kind of thing, make sure it can, the thermal can withstand that temperature. A lot of times with flange ratings, the pressure rating is based on temperature as well, so make sure you're well within the design constraints of that. Drag, a lot of times these thermal wells are in a line where process is flowing, so if that thermal well is suspended in the line, there's going to be some drag, maybe some pressure drop created. Make sure you're concerned about that. Vibration, same thing, if the thermal well is in a line, the thermal well will begin to oscillate due to the fluid flow. We'll talk about that a little bit more in the next slide. Corrosion, make sure your thermal wells has enough material compatibility, or the correct material compatibility to make sure it can withstand your process. There's a lot of guides out there to give you tables on what material works best with what process. So when measuring temperature in a pipe, a thermal well is typically installed perpendicular to the flow, and you can see in the picture on the bottom left, you can see what I'm talking about here. So the flow is going through the pipe, and you've got that thermal well suspended in the pipe, so the thermal well stem is getting hit with that flow. So that flowing process can cause thermal well failure. As the fluid moves past the thermal well, vortices will form on both sides of the thermal well, and you can see from the picture, you can see the picture on the bottom right, see what I'm talking about is vortices form on either side of the thermal well. So this is similar to kind of how the principle how our vortex flow meters work, but the shedding or detaching of these vortices subjects the thermal well to periodic transverse force that you can see in the picture. That's noted with the arrows. This force will cause the thermal well to oscillate. So as the oscillation frequency of the thermal well approaches the natural frequency of the thermal well, the thermal well does have a chance of snapping off into the process. So that's obviously a big problem. You know, if it's going to a motor or something else, you know, it could ruin your process. So some examples of this are if you go on YouTube, there's some videos of you know, light poles on the freeway when they're getting hit with big wind. You can see them begin to oscillate near their natural frequency. They can actually significantly go back and forth. Thermal well manufacturers offer a wake frequency and strength calculation. So this is typically done before manufacturing. So it's to a specific standard, this ASME standard PTC 19.3 TW 2010. So they'll take your process conditions and they'll use the dimensions of thermal well to tell you if there's a chance that your thermal well has a capability of snapping off your process. So it's a simple pass or fail. If it passes, then there should be no risk of your thermal well snapping off. If it fails, then they will make recommendations, either like by adding structure or shortening the thermal well length to make it pass and make sure that you don't run that risk of your thermal well snapping off. Okay, another consideration with thermal wells, is time response. So here are some examples to typical time response with sensors. So a thermal well obviously is going to add response time. You see a Bayer RTD, we're getting around the 5-second range depending on the diameter. With a thermal well, it goes up exponentially. You can see we get into the 20-second range. The way you can improve that, you can see there's time response and then there's a slash with HTC. HTC stands for heat transfer compound. So it's a compound they put in between the sensor and thermal well tip to improve that heat transfer, to improve that response time. So always be sure you install heat transfer compound. Most thermal well vendors, if you buy the sensor and thermal well together, they'll do that automatically. One thing to note as well, with a thermal well or just RTDs in general, or sensors in general, a tapered tip and a reduced tip improves response time, but your strength of your thermal well is affected as well. So a straight, no taper is going to be the best. Taper is going to be a little less strong, and then the reduced tip is going to be the least strong, but it'll have the best response time. So that's it for me for today. This was just a brief overview. Thank you for listening in. I hope it was informative. Please let us know of any feedback that you have to help make this better, or anything else you want to discuss, and let us know if there's any questions. We'll open it up for questions. Okay, so we're reviewing the text questions, and we'll start answering them as they come in. So one of the questions was, what is the minimum insertion in a pipe that would provide a representative temperature? That's a good question. So it depends on the design of the thermal well and whether or not you have a thermal well. So typically I think 3.5 inches is a typical size with a thermal well that would be representative of, give you a representative temperature of the process. So we'll move on to another question. And also I'm going to bring in some more people with me. I have Charles Pate here. He's our technical support manager for Field Instruments, so he's going to help me with these questions as well. And one thing I should mention, as we're looking these over, I'm going to show you my next slide. So for everyone who's joined in, we're going to do a random drawing, and 3 participants are going to receive a Yokogawa insulated tumbler. You can see in the picture here. So 3 people will contact you separately after this webinar is over, and we'll get in touch with you. So one of the questions is there a reliable method to predict response time of a temperature assembly in a thermal well if we know all the process parameters? If we have all the design considerations for the thermal well and sensor, we could probably estimate a pretty accurate response time, so we just need to get all that information, but we should be able to estimate what type of response time you should get, to the nearest second. So another question, what type of application recommends RTD 3 wires? So RTDs are good for, and 3 wires versus 4 wires actually, there's 2 questions. So, RTDs are good for a lot of applications. It's hard to say, it just depends on the accuracy that you need. A 4 wire is going to be the most accurate, but typically in industry, 3 wires are the most common. So usually that's what you find out there. So there's not a lot of need for 4 wires in industry. That's more of a laboratory requirement.
Yeah, it depends on the lead wire length too. When you're doing transmitters out in the field, you're direct mounted typically to your temperature sensor. So the need for a compensating leg is not that prevalent. So 3 wires are pretty much standard right now in the industry. The thermocouples can get you to some higher temperatures, so those are actually selected based on your temperature criteria of your application. RTDs are a little more expensive to start with, but they're more linear and a little more stable over a longer period of time. RTDs are a little cheaper, they're a little faster to respond, but they're more likely to drift off of their standard reference.
Yeah, so that was a good question. So we got another one from Mariana Cunningham. So how does Yokogawa handle the ASME PTC 19.3 thermal well calculations? Do they have a calculator that customers can use? We don't have a calculator, but we can, if you call into our support center and you give us our process information, we can estimate, we can either send off to get an official wake frequency calculation report, or we can do like an initial one that's not official to give you kind of an idea of whether or not you have that possibility of the thermal well breaking off.
Yeah, we have a quick pass-fail analysis, or we can do the full wake frequency calculation.
So the full wake frequency calculation will give you an official report that'll say pass or fail.
Along with any recommendations on how to modify the thermal well so that it will work in that application, whether it be shortening the length or making the base more stocky. So those are a couple of ways to address it.
So Robert Bland asked a good question. So does the thermal well affect the temperature or accuracy? So it's going to affect the accuracy a little bit, but not significantly. But the main thing is it's going to affect your response time. That's the big consideration when you're doing thermal wells, is you really got to be okay with the higher response time. If it's a critical application, maybe for safety, where you need a fast response time, you just need to kind of look at, there's various options, there's various thermal well options that can get you a better response time, but you always need to be aware of that.
Yeah, it's more of an issue of lag as it comes up to the temperature of the process, and as the process continues to drift in temperature for the thermal well to chase it. So it's not per se an accuracy, but it's just the time delay.
So Jeremy Randall asked a question, in what application would a stepped thermal well be preferred? It just depends, as long as the stepped thermal well, so it's like we talked about, it's not as strong as just a straight thermal well. So as long as the process, there's no danger of, it snapping off, as long as the process can withstand, or the thermal well can withstand the process, you can use a stepped thermal well and you'll get a faster response time. But yeah, just make sure you get a wake frequency report if you're concerned about that.
Yeah, there's less metal at the tip where the temperature measurement is being made by the RTD or thermocouple. So the step thermal well gives you that smaller amount of mass surrounding that, so in turn it's able to transfer that heat quicker to the sensor.
So there's another question, how does a thermal well deter sensing time? I think Charles just kind of answered that, how, the time response goes up on a thermal well. It's just the amount of material. So that was a good question. So here's another good question from Jorge Pineda. Can thermocouples be calibrated? So they can be verified, of course. So you can check to see that they're accurate. But compared to RTDs actually like that curve fitting we talked about. So you can match the specific curve of an RTD with a smart temperature transmitter. But with a thermocouple, you're not able to do that. But you can do a verification calibration with a thermocouple. You just can't. If it's out of tolerance, you can't really adjust it. So that's the main difference and why you should always go with, or if you can, go with an RTD.
And an RTD can be recalibrated later. So as they do drift, you could have it recalibrated, re-verify your Callendar-Van Dusen points, which you could use in your curve matching and maintain your accuracy, even with an older temperature sensor if you care to go those steps.
So James Albritton has a question, what do you use to perform wake frequency calcs? So we have a form that we can respond to you with. So it's basically asking you for all your process information and then what your thermal well design is. And we take all that information and use the wake frequency calculation for that. So we can send that to you. But basically it's all your process information and what type of thermal well you're looking for is used to come up with that wake frequency. All right, another question. What should I consider before procuring a new thermal well, as the gas plant I'm working with is very close to the sea and we are experiencing corrosion problems on the thermal wells? So that's a material compatibility issue. So we can't make the decision, as a company, Yokogawa, we can't, make material compatibility decisions because we don't know your process as well as you do. But if you give us your process conditions, we could possibly, refer you to a guide that could offer that material compatibility advice, and then you can make your decision from there. So yeah, get in touch with us, and we could definitely help you with that. Hey guys, keep the questions coming. We're trying to get to them as quick as we can, but yeah, These questions are really good, so keep providing feedback and more questions. And yeah, please put your questions in the Q&A window, so that way we have them all in one place and can address them as they come. So another question came in, how would you test the stability of a thermal well? When would you know when it's time to replace the thermal well? So if it's possible, if you can remove it from the process and visually inspect it. But as long as it's not, corroding away from the process, there's a material compatibility issue or eroding away. So, as the process is hitting it, there is erosion concern. As long as you can visually inspect it and make sure it's still in intact, then it should be fine. It should, last for a significant amount of time. So that was a good question. Okay, so I think we're going to end the Q&A for now. So if there were any unanswered questions, we have a list of them. So we're going to try to address them and get in contact with you if we didn't respond to your question. But again, I want to thank everyone for their time. Please give us your feedback and have a good day. Thanks.